I spend my life now telling people that the key to being healthy for metabolic health is you've got to titrate how much carbohydrates in your diet and how much you can cope with. And so those 3 athletes of the 10, on the standard diet, were eating too much carbohydrate and the body couldn't regulate their blood glucose under those circumstances. And that's going to harm them. They will become diabetic once they keep on that diet for 10 or 20 years. They will become diabetic. Mm-hmm. Now, do they represent all runners in the world? I would say they probably do, that 30% of runners eating this high carbohydrate diet in their 30s or 40s, if we tested them properly, we'd show that they're pre-diabetic.
Professor Tim Noakes, thanks so much for joining us here on A Whole New Level. I'm really excited to dig into some of the concepts of metabolism, metabolic fitness specifically, including our research collaboration on a lot of those things that we recently had published. So thank you again for joining us.
My pleasure, Josh. Lovely to be with you. Thank you.
Awesome. Well, you know, your career has spanned many decades and covers the whole spectrum of metabolic health, as well as fitness and fitness adaptation under different metabolic circumstances. And I'm really excited to speak kind of initially about your recent work, which Levels had an opportunity to be a part of, which focused on adapting to low-carb, high-fat diets for recreational male athletes. So I'd love to hear your summary of that recent work, and then we can kind of dig into how those findings apply to certain groups.
Sure. So let's go back to the history so people have got my involvement.
Perfect.
So I started doing sports science in 1981. That's when I really became committed. And the first thing we studied was hypoglycemia during exercise, because I was sure that hypoglycemia developed during exercise. And at that time, people were being encouraged even not to drink water during marathons. It was quite a long time ago and quite different. And so we started experimenting, and our focus was on the Comrades Marathon, which is 90 kilometers. And it became very clear that some elite athletes developed hypoglycemia and really struggled. And then there were examples of where they took carbohydrates and were able to finish the race comfortably, having slowed down, and then they take the carbs and then they do well. So together with Bruce Fordyce, who was in fact probably the greatest Comrades runner in history, we developed a product called FRN. Fordyce, Rose, was the marathon runner, and myself. And so that was the first goo that people used during exercise. And so I was totally committed that carbohydrates were essential for exercise. And I bought into the idea that muscle glycogen depletion causes fatigue during prolonged exercise. So I went along with this and wrote the book Law of Running, and it's all full of carbohydrates. You must eat every single carbohydrate you can see, you must eat, and you must load up on carbohydrates. And the last time I wrote it was 2002. Now, my career took a major change in 2010 because I learned about the low-carb diet. And I read Eric Westman and Jeff Volek's book, and that convinced me in 2 hours that I was completely and utterly wrong in what I was doing and saying. So I changed that day. And within 4 months, my health had improved dramatically. I'd lost a lot of weight. My running was improving. And I started telling people that, listen, I've gone to this low-carb diet. Here's the guy who's promoted the high-carb diet, and I've now gone to a low-carb diet. And I wrote some articles, and the first response was I lost all my funding, like that. And I was killed. I was dead in the water. Wow. So, and then my university kicked me out. Well, they didn't kick me out, but I just retired, and they exposed me in the press and say I was no longer believable, because I was promoting a diet on the grounds that it reversed type 2 diabetes, and that was a ridiculous claim, and so on. And then I had to go to court to fight for 4 years, because what they'd done, they tried to destroy my career. Now, during this time, low carbs, my type 2 diabetes reversed, and eventually in 2018, I won the case, and it was all over. And for once, I'd actually learned a bit about nutrition. I thought I knew about human nutrition, but I really didn't, because in medical school, we don't really learn it. And I'd maybe studied carbohydrates during exercise, but I didn't understand the whole body nutrition. So then what happened was Philip Prince and your guys came and spoke. Philip phoned me or wrote to me and said, Tim, I'd really like to do some research with you. I met him, I think, in Ohio at Jeff Ehrlich's conference. And he said, what should we do? So I said, well, let's do a 5K time trial, because your team is really good at doing 5K time trials on the treadmills. So I said, let's do that and see what they burn. And so I honestly didn't think that we'd find the result that the 5K time trial was identical. We'd also done a VO2 max test before and at the end of the trial on both diets. And I looked at Jeff Ehrlich's book, not his book, but also his research, and particularly the FASTER study, because he'd also done VO2 max testing. I thought, I wonder if he's ever looked at the so-called crossover point, the point at which you start to burn more fat than more carbohydrate than fat. And he hadn't done it. So then I said, well, why don't we just look at those data? So Philip did that and produced a really good paper showing that the crossover point shifted far to the right to about 85% VO2 max, which is when you're not meant to be burning any fat. So we published that one. And then the most recent paper, I said, well, okay, if it works at 5 kilometers, maybe it'll work at 1 kilometer, because that's a real test. So we did the 1 kilometer time trials and found no difference. But I'd warned him. I said, but if you find no difference, what the people will say, it's because the athletes had lots of glycogen, even though on low-carb diet, they had enough glycogen for 1K or 1 mile.
Just to clarify for those listening, so what you mean by no difference, it's no difference in performance on the 1 kilometer time trial between the high carb, low fat, and low carb, high fat groups.
Correct. Thanks for clarifying that. Then I said, so why don't you do 6 times 800 meter repetitions? But I didn't say, and he decided to do this on his own, I didn't say measure oxygen consumption and metabolism, which was the key thing. So anyway, surprise, surprise, there was no difference, because what should have happened, according to the traditional hypothesis, after about 3 sprints, 800 meter sprints, their performance should have gone down in the low carb group because they've got no more glycogen left. You can predict they'd run out of glycogen after about 3 800 meter repetitions. It didn't happen. They stayed exactly the same, regardless of diet. But then the real killer was that they measured the oxygen consumption and the respiratory quotient, from which we can calculate, as you know, carbohydrate and fat oxidation. And the fat oxidation just went up and up and up and up and up. So the more repetitions they did, the higher the fat oxidation. And by chance, they were exercising at 86% VO2 max. And the textbooks say at 85% VO2 max, you burn no fat. That's what the textbooks say. The highest rates of fat oxidation in history, exactly at the point where they're not meant to be burning any fat. So
it's fascinating. So
what that shows is that muscle glycogen doesn't have an obligatory role during exercise performance. There's no obligatory role.
Even at these high intensities, which is really the focal point here. Yeah. Correct.
And so therefore, when one goes back and looks at the original studies, which claim that there's this specific obligatory role for carbohydrate, for muscle glycogen, by chance, I'd done this before the studies, so I knew that the evidence was there. In those original trials done by the Scandinavians in 1967, they showed that at the point of exhaustion, even though the guys had low muscle glycogen, their blood glucose levels were incredibly low. So they were all hypoglycemic. And you won't believe it, but yesterday, I looked at those same studies and I looked at their metabolism at the point of exhaustion in people eating a high carbohydrate diet, mixed carbohydrate diet, and low carbohydrate diet. And there were big differences in muscle glycogen at exhaustion, which doesn't fit the model. There were big differences in fat oxidation at exhaustion, which doesn't fit the model. And there were big differences in carbohydrate oxidation. But the one thing that wasn't different was the blood glucose concentration. And so you need to look at the variable that's not different. That is the same, because that's what is going to be the limiting factor. And it was very clear that it was blood glucose. I then went and looked at a whole bunch of other studies. And I now know that when you take carbohydrate during exercise, or you carbohydrate load before exercise, all that happens is during exercise, you substitute a little bit more carbohydrate for a little bit less fat. And the kilojoules are absolutely matched. So if you burn an extra, let's say 5 or 8 kilojoules per minute, which is a trivial amount, it's a trivial amount of carbohydrate, you burn 8 kilojoules of fat less. And what we've been told since the 1980s, since the sports drink industry got involved, they said, without measuring it, they said, but that's the difference. It's this extra carbohydrate that you're burning in the muscles that makes you perform better. But so now if someone must tell me why burning 8 kilojoules per minute more of carbohydrate, which is only 10, 15% of the total energy that you're expending at that time, why is that so special that you couldn't make it up with fat? And what we've proven now is that you could make it up for fat, but what was happening was these people were hypoglycemic. And that's, if you take carbs, you can go longer because your blood glucose is higher and your brain still functions. That's what I know. And it's so I'm working very hard on a couple of articles which really definitively show that it's blood glucose which is the obligatory fuel. It's not muscle glycogen.
It's fascinating, and I think we went pretty deep there, and I'm very excited to kind of break that apart a bit more for people. So showing that these assumptions that have been around from the beginning for many of us of our exposure to the sport, these assumptions were ingrained like law about what the body needs in order to perform. And finally, having better tools, better techniques, and honestly, better questions to then go and explore is really interesting because it's overturning many of these laws. So I'd love to hear a little bit more. So let's dig into, for people that are listening who aren't as familiar with the metabolic concepts here, essentially there are two fuels that we are running on. We're running on carbohydrates and we're running on fats. And what we, through this research, are seeing is that the body can adapt from the carbohydrate reliance towards the fat reliance at all intensities of exercise. It used to be believed that above a certain threshold of effort, you have to run on carbohydrates. And you've now shown through your research that that is not true. Now, what I'm interested in is there is that limiter that you brought up at the end, which is the transition to blood glucose as the limiting factor. And a lot of us think of glycogen and blood glucose almost as proxies for one another. So can you break this down for us? What's the difference here and what's happening?
Sure. Now, and when I started looking through this literature, I believed exactly the same as you. And what we do as physiologists, as you know, we say it doesn't matter if it's the carbohydrates coming from the muscle or from the bloodstream, the regulation is the same. And that's totally false. And it took me a long time to realize it. So what happens during exercise, your muscle glycogen drops down as a sort of linear function of the duration, which tells you largely that the exercise is regulating how much glycogen you are using. But it's going down. It's always going down. I did not know until 6 months ago that the glucose that's coming out of the liver into the bloodstream is now circulating to the muscles and it's getting used by the muscles. But the regulation is totally different. Why? Because blood glucose oxidation just goes up, increases. And that's paradoxical because you don't really want that to happen because the poor liver is becoming more and more depleted of glucose and glycogen. It's having more and more difficulty to produce glucose. And the muscles are saying, I don't care about you. I want that glucose. And ultimately, you will always reach the state where the muscle demands more glucose than the liver can provide, and your blood glucose will fall. Now, the brain's not so stupid that it says, okay, the blood glucose is falling, we must just continue until you die, because the glucose in the bloodstream is crucial for all the brain function. And so the brain has a protective mechanism. And in all these studies, you can see as the glucose starts to drop, the power output of the athlete starts to drop as well, and they start to get the fatigue symptoms. But if you give them glucose, after 10 minutes, their glucose starts to rise and they feel fantastic and they can go on for a long time.
Mm-hmm.
So it's very clear to me that the regulation is different. And then the next question is, why is the regulation different? And I'm now speculating. So what we've shown, and you've been crucial to this as well, what we've shown is that the blood glucose is crucial, and that the body will burn the glycogen, but it could burn fat for everything. So why doesn't it?
Mm-hmm.
Why doesn't the body just burn fat? And one of the keys that I observed was that in the studies where people are studied at rest, 50% of the energy is coming from carbohydrate. Now, that does not make sense, because this is the jet fuel that the body's trying to conserve, and that's why you're filling your mouth with carbs to provide the muscles with carbs and glycogen. And the body's wasting it by burning it at rest and when you're sleeping. Why? And the answer is very simple. And it's provided by George Cahill, who wrote this in 1971. He gave one of the famous lectures in 1971. And he said the first rule in metabolism is that the body regulates the blood glucose concentration and keeps it within a narrow band. And everything's focused on that. And as soon as the glucose goes out of sync, the body responds dramatically to try and get it back into range. The one way you can get the glucose back into range very quickly is you dump the glucose somewhere and you dump it into the muscles. And then the body is so clever that it says, okay, we've got too much glucose or glycogen in the muscles. I know you're going to go out and have another Coca-Cola and you're going to have some chips and bananas in 3 hours' time. I've got to anticipate that. I've got to get rid of this glucose in the muscles so the next load that comes in, I can store it. And that's what's happening. The only reason you burn glucose is to regulate your blood glucose concentration. That's why you burn glucose. What happens in the body is that the muscles respond. And if they've got lots of glucose, they will burn glucose. They have to. And the only way you can stop that is by not eating carbs. Then your muscles are full of fat and very little carbohydrate, and then you will burn fat. And something which I didn't really catch on to until 2 years ago, we studied an athlete who was a low-carb athlete, but he was a really good athlete. And so that he could cycle at a very high rate from the moment he cycled. And we had him do a 100K time trial. And from the instant he got on the bike, he was burning 1.7 grams of fat per minute, which normally, as you know, if you're carbohydrate adapted, you would never get anywhere near that. But if you're carb adapted, you start at 0.4, 0.5, and it takes you hours and hours and hours to get anywhere near. But the moment he was burning 1.7. Well, we subsequently did studies to prove it, that the content of muscle glycogen determines how much fat and carbohydrate you burn. So now the final little story. So I went back to those original studies, the 1967 studies, and I looked at the group who were on the low-carb diet. And although they could only exercise for about an hour, they had a rate of fat oxidation which was higher than anything that had ever been reported. But they didn't notice it because they were focusing on the carbs. Yeah, and so from the word go, they were burning a whole lot of fat. Now, they were not fat adapted, which is the other interesting point. These people were athletes or probably just general people.
Well-trained.
I think they were policemen or something. I can't recall what they were. But they were burning fat even without being fat adapted. And so what do I interpret that to mean? That I interpret it to mean that the body's designed to burn fat. And the only way you don't burn fat is if you're eating a high-carb diet. So the natural state is to burn fat. You don't need to train for it. It develops And Louise Burke has shown that. She took some Olympic athletes who were high carb athletes. Within 5 days, they were burning 1.6, 1.7 grams per minute. They didn't need to go out and train.
So the theory is kind of evolving towards what we're seeing is actually an adaptation towards carbohydrates that we've induced. We think it is the natural state, but actually it might be that that's upside down. And in fact, the natural state would be fat oxidation. And I have a question that I think will lead into this in just a minute that I would like to get into to kind of determine what nature's preferred fuel substrate is and why. And I think there's an interesting question buried there. But one last thing I wanted to touch on that we kind of mentioned and moved past is the question of why doesn't the body just burn fat even when fat adapted, right? So even when we really fat adapt, we will never go to zero glucose in the bloodstream. We'll always be producing glucose and maintaining it in that very tightly regulated band that George Cahill was describing. And can we answer that for the listeners? Why is it that the body will never get to, even in the most fat adapted state, after 30 years of eating, a high fat, low carb diet, will we never get to zero circulating glucose?
Okay, because glucose is obligatory for the brain. And that's why I think that the glucose oxidation goes up blood glucose oxidation goes up during exercise. That shows it's obligatory. You can do what you like, you can't stop it. You can take all the carbs you like, you won't stop this. It's going to go, and you can start exercise carbohydrate depleted, and the rate of blood glucose oxidation is the same. So it's fulfilling some obligatory role. And obviously part of it's brain, some of it may be kidneys, some of it may be other tissues. And it may also be obligatory for muscle. I'm not going to exclude that, but it's such a tiny amount that it's not as we used to think that it's the predominant source. It's a tiny, tiny amount. And I'm not excluding the possibility that you need a little bit of carbohydrate to keep muscles working properly.
Yes. Thank you for clarifying that, because I think that's a really crucial point, which is that we don't want to get overhedged in one direction or the other. And the fact is that we have been in one direction. As somebody who has tried to train in various ways over my lifetime and trying to sort of replicate what I see the elite athletes doing, assuming that that's what's best, it really leads you to a very carbohydrate heavy fueling strategy, because that's really, you see somebody in the gym or on, training for the Tour de France pipeline, and the way that they're consuming calories, the vast majority in those training cycles are carbohydrates. And so people, we have this tuned, the whole culture is oriented around that. And it's not that we should overcorrect in the other direction. It's that, in fact, the science probably shows that we've adapted to operate in that environment. And we should likely, we need to understand what the natural adaptation is. And we know, however, that glucose will never go away. It's always going to be, a critical element for brain fuel. And the interesting thing, I think, is also, we think about the brain and how it has a critical fuel dependency on glucose, but the heart has a critical fueling dependency on lipids, on fats, right? I believe the muscle tissue in the heart almost exclusively oxidizes fat. Is that correct?
It's really interesting because my PhD was actually on little rat hearts, which we got to contract. We had them pumping as if they were in the animal, and we stressed them. I developed a system for testing them to their maximum output. And I measured what their fuels preferred. And the answer was it was glucose and insulin were actually the best, but ketones worked also very well. The problem in the model, it's difficult to study fat metabolism because for various reasons, we have to bind fat to albumin, and that changes the whole characteristics of the fluid that you're pumping, that the heart is pumping, and it changes the dynamics. But glucose and lactate and insulin and ketones, the heart loved all of them. It just depended what you give it, it will burn. Yeah.
Okay, so it's hyper flexible. Well, I think that to kind of shape the conversation a bit further, I'd love to talk a little more about the findings and how you would say these apply to various groups of people who are likely listening to this conversation. So this group was specifically recreational male athletes that we studied, and I know there's a lot of research that goes in with various demographic cohorts. But how would these same findings, in your opinion, apply to elite athletes? And then I'd like to also hear from there how you think it would apply to female athletes specifically.
Okay, so let me answer that question. Firstly, you're quite correct because you saw the athletes and you know they were recreational, but they were actually better than 88% of all American runners. So although they're recreational, they're elite recreational athletes. And so therefore, 88% of American runners, and that applies to runners across the world, I would think, could benefit from this diet. They didn't need to eat the high carb diets. There was no difference in performance. So now you say, okay, what about the other 12%? When you look at Eliud Kipchoge and he runs his marathon in 2 hours, I'm rewriting law of running, and I came to realize that it's pointless saying, oh, he's running at a VO2 max or a VO2 of such and such. What you want to know is how many kilojoules per minute is he expending? And where are those kilojoules coming from? And it turns out that because he's only 52 kilograms, he's actually only burning 78 kilojoules per minute, which is 2 grams of carbohydrate, so 2 grams of fat per minute. So technically, he could run the marathon on fat if our model is true. The problem is that he's been raised on a high carbohydrate diet, and the Kenyans run on a high carbohydrate diet because that's what's available to them. But I will guarantee you that their diet has changed in the last 100 or 200 years. That 200 years ago, many of those African runners came from generations who were cattle rustlers, and they were eating an animal-based diet, I would guess. And it's only more recently that they moved to a high carbohydrate diets.
Yeah, which I mean, it demonstrates the pretty amazing flexibility of the body to be able to perform, right? And whatever the sort of environmental circumstances provide. So that's really interesting.
Butt in for another second.
Sure.
So one of the other studies I looked at in detail was the first study to show that carbohydrates ingested during exercise could improve performance. And it was a study written by Ed Coyle, 1986. And we published another paper in 1986 trying to prove that hypoglycemia could be reversed in performance. And we couldn't find it because our model was wrong. He got into the laboratory and did the best way to do it. He starved the people for 12 hours before exercise. That was the key. But I went back and worked out the metabolic state of those athletes as well. And I noticed that they didn't report the actual fat oxidation rates. They reported the carbohydrate oxidation rates, and they had a picture showing carbohydrates, fats, and muscle glycogen oxidation. When I made the calculations, I showed that these people were the ones, when they took carbohydrates, they were burning fat at 1.2 grams per minute, which was the highest value ever reported at that time. And no one noticed it. So who were these athletes in 1986 who were burning so much fat? The answer was they were Olympic class elite cyclists in Austin, Texas, from where Armstrong arrived. Lance Armstrong comes from there. So they're obviously very competitive. Ed Coyle got some of the best cyclists, and they were fat adapted in 1986. Why? Because that was before the carbohydrate craze hit. I think that was the one reason. Secondly, because they go out and do long cycles. And I'll bet if you studied the Tour de France cyclists, although they're eating high carbohydrate diets, because they cycle for 5 or 6 hours frequently, they fat adapted as well. So that study showed people eating a high carbohydrate diet could be fat adapted. And clearly they were doing some training that wasn't being done by everyone. And a runner can't run for 6 hours. So a runner is less likely to be fat adapted than a cyclist, in my opinion.
When you say a runner can't run for 6 hours at a certain intensity level?
I'm talking about training. I mean, I think the Tour de France cyclists, the hardest, they spend the most time on the bicycle. So they are going to burn through carbohydrates and get into that fat burning zone much more frequently than runners.
It's essentially that, given this certain exercise domains, you can essentially outpace the dietary substrate that you are working from, and then your body kicks over into the adapted state, depending on which, on a bike, you can produce 350 watts of power continuously. You don't need to, and most people do not do that when running. Like you said, with Eliud Kipchoge, he's he's burning, his actual power output is actually quite low, given that he's, does not weigh a lot and he's kind of moving very efficiently. So it's really interesting.
So one of the first people who contacted me, one of the first elite athletes contacted me was Dave Scott, who won the Ironman 5 or 6 times.
Mm-hmm.
And he said, Tim, if I'd followed your diet in the 1970s, I would have gone 40 minutes faster in the Ironman. He said that was the worst mistake he ever made, was to eat the high carb diet. And there's another lovely story that Paula Newby Fraser, who won the Ironman 8 times and who won 28 Ironman triathlons, she's actually from South Africa. And she was such a talent. She went to America after 1 year of training, came 3rd in the Ironman the first time. And then that was in 1984 when Steve Finney's first paper came out saying you burn more, eat more fat. And she phoned me and she said, Tim, I've read this paper. What do you think? Should I eat more fat? I said, yes, Paula, eat more fat. But at the time I was promoting the high carb diet, and she interpreted it as she should go on a low carb diet. She went on the low carb diet. She won all these Ironman. And when she retired, she said, the best piece of advice I got was to eat the low carb diet. And I said, Paula, but I never told you that.
What a funny coincidence. That's wild. Yeah, well, that's a great transition from, elite athletes and specifically female elite athletes, and how clearly that was a success story for her. How about if we take the recent results of the research and discuss, how do these results, which were entirely male recreational athletes, how do you think that applies to female athletes? Do the same, the same sort of biochemical principles we discussed here hold for both sexes? And what do we? Yeah, I'd love to hear your thinking there.
So when I was running marathons more competitively in the 1970s, there was a guy called Dr. It wasn't Atkins. He was a German doctor, and he came up with a theory. And he said women are going to outrun men. And why was that? He said because women burn more fat when they're running, and they'll have better endurance. So that was the theory in the 1970s. And I don't know if it's been shown since then, because I think you burn fat on the base of your diet. So he was probably studying women who were eating more fat in their diets. I can't see any reason why the women's muscles would be different and would metabolize any differently than men, as far as the energy metabolism goes. Mm-hmm. So I would think it applies to women. But what I would like to say is that having developed type 2 diabetes as a result of following this low-carb diet, following the high-carb diet, and running 70 marathons or ultra marathons and still getting type 2 diabetes, I'm a bit more suspicious about the health effects of the diet. And the study that we did also showed that 30% of these recreational athletes became pre-diabetic on the low carbohydrate diet. Whereas when they were eating the high fat diet, low carbohydrate diet, so let me get that right again. When they ate the low fat, high carbohydrate diet, they became pre-diabetic. When they ate the high fat, low carbohydrate diet, their control was absolutely perfect. And Andrew Kutnick, who was crucial in this analysis, showed that those athletes who burned the most fat were the ones whose glucose control improved the most when they went on to the high-fat diet. So that was the first time linking fat oxidation in muscle with more resistance to type 2 diabetes or pre-diabetes. And the other very important point from that study, the first study showing pre-diabetes developing without people putting on weight, changing their diet, or changing their exercise habits. The only thing they changed was the diet.
And this is shown through the continuous glucose data that the athletes were developing so it was a crossover trial. So essentially we had a low carb, high fat group and a high carb, low fat group. And then they crossed over at the midpoint. So they each did that diet for 4 weeks. Then they switched and did the other diet for 4 weeks. And so what you're describing there is an actual onset of these abnormal glucose dynamics as tracked by a continuous glucose monitor during the high carb, low fat portion. Is that right?
That's correct. So, I spend my life now telling people that the key to being healthy for metabolic health is you've got to titrate how much carbohydrates in your diet and how much you can cope with. And so those three athletes of the 10 on the standard diet were eating too much carbohydrate, and the body couldn't regulate their blood glucose under those circumstances. And that's going to harm them. They will become diabetic once they keep on that diet for 10 or 20 years. They will become diabetic. Mm-hmm. Now, do they represent all runners in the world? I would say they probably do. That 30% of runners eating this high carbohydrate diet in their 30s or 40s, if we tested them properly, we'd show that they're pre-diabetic. And, you know, the other thing which people don't perhaps understand, but when we started running in the 1970s, you trained really hard. And at the end of 3 hours, that was the end of the race. I mean, if you hadn't finished within 3 hours, there was no one hung around to see you finish in 6 or 7 or 8 hours. They were gone after 3 hours. And everyone was lean, but really lean because they trained hard, but they didn't eat so much carbs. Now you go to these marathons and you see that people finish in 6 hours. They're a metabolic disaster. You know, they're carrying all this extra fat, but they believe because they're running, they're going to be healthy. And that's not true. And then we are telling, not we, but others are telling them to eat high carbohydrate diets to run faster. Mm-hmm. So to get back to your point, I would say that the only people who can eat high carbohydrate diets as runners is those who prove they're not pre-diabetic or not going to become pre-diabetic. You have to earn your carbs by being healthy. If you're not healthy, and it's as simple, if you've got visceral obesity, if you've got a tummy and your waist is too wide, carbs are killing you. And people have to understand that, you know, and the reason why I'm so vocal about this is I watched my dad die from type 2 diabetes and I couldn't help him because I didn't understand. And it is an awful, awful death. And that's, in a sense, why I came out and said I was so wrong about the diet, because I knew that a lot of people will become diabetic if they follow the dietary advice I was giving. And I had to say, listen, I'm terribly sorry, I was wrong. I don't want you to die. I don't want you to be sick as a result of this.
So I want to do two things here. Firstly, try to draw a distinction between all carbohydrates and the ultra processed stuff that people tend to, you know, if you look at the world of sports, as somebody, you know, at my fittest point in my life, in my mid late 20s, I was working out, CrossFit trainer. I had a lot more muscle on than I do even, you know, now, and I'm in decent shape now. And yet when I first used a continuous glucose monitor, I immediately recognized that I was pre-diabetic. I mean, my blood sugar was quite chaotic. And what I was doing was following, again, the best practices of the sort of sports science around me, which was a lot of very processed carbohydrates before workouts to carb load, a lot of processed carbohydrates after workouts to glycogen replenish were the terms I was using, a lot of sports drinks that are loaded up in very fast metabolizing glucose and fructose. And so I was constant bombardment to my system, and my body just simply couldn't keep up. And even though I was not showing the visceral adiposity, I wasn't showing any of the signs that you would look at and say, oh, that person is at risk for diabetes or prediabetes. My blood glucose dynamics were horrendous. And so I've done a bunch of things personally. And again, this is an N of one, but I've gone all the way to the other direction, ketogenic, lots of running, lots of zone 2, lots of fasted exercise, which I would love to touch on in just a minute. And now I've come back and sort of balanced where I, like you're saying, titrating the carbohydrates and very, very specifically picking the carbohydrates that I know I can trust, the ones that are not going to be an assault on my bloodstream. They're going to break down in the context of fiber, in a whole food, you know, and this tends to be berries. It tends to be, you know, sweet potatoes or something like that. Every once in a while, you know, I'll make some rice or even some pasta when I want to indulge, but I'll be very careful about what grain varieties I pick. And anyway, all that to say, I do so, and I pick the portion size based on how active I've been, how much I'm expending, how much my body is sort of depleted. And I think that's maybe an important point. I would love to hear your thinking on that. You know, when we're talking about carbohydrates, how much are you indexing on the type of carbohydrate, the processing, versus just the overall sort of macronutrient itself?
Yeah, I think you've made all the valid points that you need to make, that you have to be very cautious and not eat ultra-processed foods. So again, very important advice. What I do think one of the problems with ultra-processed foods is the addiction, and that's also a problem. To me, obesity it's largely based on addictive foods, and the ultra-processed foods are designed to addict you. So that's one of the problems. So if you're running, and what you said is that depending on how much you're running, that's fine because you burn off the carbohydrates. And it's really interesting that when I was running ultra marathons, I was clearly pre-diabetic, because the only time I would start to feel good was after running about 4 or 5 hours. And then I think I went into ketosis, and my glucose finally stabilized and my body felt much better. Doing a little exercise didn't help. It had to be a really long exercise. And then when I trained really hard, up to 150 kilometers a week, then I felt good, because now I was burning all this carbs, was just going out of the body. I was burning it immediately. The minute I stopped, I couldn't believe how quickly I would put on weight. It would just within a month, I would have put on 3-4 kilograms. I couldn't believe it. Yes, and I now understand why, because I couldn't regulate my blood glucose. So it was just packing the carbohydrates into fat. Yeah.
It's so interesting how quickly these things change. And I think let's talk a little bit more about the glucose dynamics during exercise. So a lot of people that are listening to this have likely tried a continuous glucose monitor themselves. So they're listening to the results of the research that you showed, which show that with high fat, low carbohydrate diet, high intensity performance is not reduced relative to high carbohydrate, low fat. And the glucose dynamics that we saw, we sort of touched on this a bit, how glycogen reduces in the muscle, how glucose trends in the bloodstream. Some people who are using CGM see varying results. I myself, at a certain intensity level, start to see my blood sugar dramatically increase. And so I'll have, in some cases, over 200 milligrams per deciliter, what is that? That's like over 10 millimoles of glucose in my bloodstream just from a workout, fasted. And that's a very high intensity. So can we touch on that a little bit more? How should people, what's going on there? And then also, how should people think about those glucose spikes in the context of their overall health?
I think that people who are pre-diabetic are the ones who will raise their glucose during high-intensity exercise. I noticed that on myself when I was a 28-year-old. We were doing studies in believe it or not, low-carb diets. And on a high-carb diet, my glucose shot up during exercise, and it shouldn't do that. Even during prolonged endurance-type exercise, which wasn't high-intensity, my glucose rose. And I didn't spot it because all the data I had seen up to that point said that the glucose stays normal during prolonged exercise. So I knew that I was insulin resistant. And so I've kind of interpreted that to mean that that's actually a marker of the pre-diabetic state.
Interesting.
So it's even more reason why you need to keep your carbs down if you see that spike during high intensity exercise. Do I think it's serious? Probably not. It's the sustained glucose with the high insulins. One of the other things I've learned in the last few months looking at the data is what is astonishing is how quickly your insulin drops during exercise. You can start with an insulin of 60 units, which is extremely high because we're trying to get down to 6 units in the units we use. So it can be 10 times normal, but it will be back to normal in 10 minutes of exercise. So the best way to lower your insulin, apart from not eating carbs, is actually to exercise. So I would think that although your glucose is going up, your insulin's coming down, and probably the insulin is more of a problem. And also, high intensity exercise didn't last too long, so you probably won't have high glucose for too long. So to summarize, I would say if you're getting a high glucose during exercise, you're pre-diabetic probably, but we're talking about 20 years forward. We're not talking about tomorrow. Mm-hmm. And you're just an insulin resistant person, and you need to interpret that appropriately.
So should people expect over time, given, let's say, the same intensity, if they were to adapt to fat oxidation, so start eating a higher fat based diet, should someone expect that those glucose spikes would reduce over time given the same intensity?
Yeah, that's what one would assume. And again, from the data that we have, we saw a normalization even during exercise. There was a greater return to normal. So I would expect that. I can't see why, if you're not eating too much carbs, you should have these abnormal glucose spikes.
Yeah. So, from my own kind of N of 1 research on myself. I will say that I've seen a reduction over time in the sort of absolute peak of those high intensity spikes. So I'm going to have to dig into this a bit more and see how that trend is looking. We're short on research on this matter, but ultimately it does look like, well, first of all, we know fundamentally it's totally different to be experiencing elevated glucose from sort of sitting on the couch drinking a Coca-Cola versus pushing weights around or running at a high intensity. So, just what's happening biochemically in the body is totally different. And I think that the insulin level that's a great way to think about it, is your insulin also being elevated?
By the way, I've just had this thought. So I must tell you that the guy who set the new world record for the Ironman, that setup where they had guys helping them, and I think he did under 7 hours. He showed his blood glucose concentrations, and they were all over this. They were unbelievably elevated. They were pre-diabetic. And he said, see, I'm never going to become hypoglycemic. I realized, actually, your problem is hyperglycemia. Man. So he must have been loading up on the carbs to great excess, completely unnecessary.
I wanted to jump ahead into one other question that I know is going to be top of mind for listeners, which is the low-carb, high-fat exercise versus fasted exercise. So how, a lot of people are now, myself included, including and incorporating fasted exercise into our routines. I personally feel really good when I'm going to do, say, prolonged zone 2 exercise, doing that fasted versus doing it after any type of meal. High fat, low fat, doesn't really matter. How do you think about fasted exercise in the context of adaptation and improving metabolic function, metabolic fitness?
Well, I just think fasting is really healthy, and combining it with exercise would suggest to me that you've got a double benefit. I don't have any evidence that that's the case, but I do know that fasting is one really good way to help reverse metabolic syndrome. So I think that stressing your body in those two ways is very helpful. You see, the irony is the greatest threat to the body is not starvation or fasting, it's high carbohydrate diets. And people don't understand that. By the way, by starvation, I mean a few days of not eating. But the thing the body can't cope with is a high carbohydrate diet. It can cope with fasting. The world record for fasting is like 380 days. But that guy he had a lot of fat on him to burn off.
Yeah, it's a fascinating story. So I think his name was Angus Barberi, and just took in minerals and water for 380 something days, and yeah, really fascinating. So I think that the evidence is very clear that it's, fasting is not an acute danger. Of course, considering the individual circumstances, and everybody is at a different starting point, and hormones also really play a role here. And I would love to jump into that in just a minute. But stepping into the next question here, as I know I want to be mindful of your time. One topic that has come to my mind repeatedly when thinking about why the body does so well in low carb adaptation is, did evolution select for the most efficient fuel by default? And what I mean here is, for each gram of fat, you get 9 calories of energy. And for each gram of carbohydrate, you get 4 calories of energy. That means that if I'm the body, I'm evolution, trying to figure out what fuel should this body carry around with it, what's going to be most efficient? Well, I'm getting 2.2 times more energy per gram of fat that I carry. So we now know that when you look at an average person, let's say someone who weighs 150 pounds and is 20% body fat, that person is carrying over 100,000 calories of fat energy. And if they were carrying that same body weight in glucose or glycogen, they would only be carrying about 30 to 40,000 calories. So it would be much lower efficiency in terms of like you're carrying that weight around and how much energy it contains. Is this something that you think about? Does that factor in at all? And how do you think about like the evolutionary context for why the body prefers which substrate?
So I'm sure we all have the same slide, which is how much carbohydrate you store in the body and how much fat you store. And and then you look at that, and that's the great question you're asking. Why do you store so much as fat? And then what you didn't mention is when you store the water, carbohydrate, you store water with it as well. So that and I used to think that was the reason that you can't store much energy as carbohydrate because it's full of water. I think that evolution adapted us to eat high fat, high protein diets. And there were 2 papers published in the last month. And the one was 120,000 years ago, And they showed amongst the fossils that they were looking at were elephants. And they looked at the elephant bone, which is the foot bone. So it's like the toe down there. And below that, the elephant has a huge pad of fat. So but it's a big bone like this, and below it's a lot of fat. And humans obviously like fat because if you looked at the bone, it had cut marks on it. So humans had specifically gone and cut the bone, cut to get the fat away. But it was an elephant. 120,000 years ago, humans hunting elephants. How did they do that? They didn't have guns. So they did something very clever. But now, the last paper came out also, I think last week, 3 million years ago, Paranthropus, who was one of our predecessors, not yet human, was killing rhinoceroses. So they found rhinoceros bones with these cut marks showing that humans had taken the meat off these bones. How do you kill a rhinoceros when you're Paranthropus, and I guess is probably 5 foot tall? But the point was, that's what we grew up on. We grew up on fat and protein diets. And that's why we developed the gut and our brain as well. So I think we've been adapting for this for 3 million years to be adapted to burn fats and not carbohydrates. Carbohydrates, as you know, come into the diet 12,000 years ago with the agricultural revolution. And they came in because we ran out of fat animals on all the continents. We just didn't get enough fat. So now we had to find something else. And we couldn't eat lots of protein because our bodies are not designed to cope with too much protein. So what was obvious we had to get was some carbohydrate. And so that became cereals and grains.
Yeah, I think looking at the timescales and the availability of first of all, carbohydrates that scale throughout the year, right? I mean, that is very seasonal to be able to come across, high carbohydrate foods, but just even if we look at carbohydrates as a basis of energy for tens of thousands of years, probably maybe even hundreds or longer, if you consider that time scale, the past 100 years is still a black swan event in terms of how much processed sugar and carbohydrate we can get into the bloodstream in how much time, right? In 15 minutes, I can consume more sugar direct to the bloodstream in a liquid form or in a powdered form than most of our predecessors would come across in months or years, maybe. So I think that's I think it's unequivocally the case that we have exponentially increased the load on our systems. So I have two final questions.
And just one other point: the populations who converted to high processed foods, if you come to Africa, the populations that started eating sugar and refined carbohydrates, they destroyed their teeth. They didn't have dentists, so they couldn't survive. If your diet kills your teeth, you're finished because you get brain abscesses and so on. So we know that going back far enough, they couldn't have been eating a lot of carbohydrate, or they would have had terrible teeth.
It's such an interesting, and we can spend a long time on the history here, but I have two more questions that I would like to take just sort of in almost a lightning round style. The first one is, what's the most important question you think researchers need to answer next in terms of fuel adaptation, low carb, low fat? What is the question that's burning in your mind on the research side?
Okay, what's burning on my mind is to get people to accept the data. And the only way we can do that is by having lots of people who previously promoted high carb diets doing research and proving that they were wrong. That's what we need to do. Problem is that's not going to happen because the industry funds people to study carbohydrates. And that's partly the reason why carbohydrates are so dominant. And I'm party to that because we were funded by the carbohydrate industry for 15, 20 years. And we did fabulous studies, which I now realize were really amazing. But they were all looking at carbohydrate metabolism. And only right at the end did we do some studies where we did low carb studies. And they were critical. They were absolutely critical because they showed where the controls were. The controls were that if you had high muscle glycogen, you burn carbohydrates. If you have low muscle glycogen, you burn fat. And even insulin isn't the main driver. It's what's in the muscle at the start of exercise. Insulin helps and glucagon helps, but it's the driver is in the muscle itself. So I think that's what I'd like to see, because I think runners are getting the wrong advice and their health's being affected, as my health was affected. And I would just wish that I'd known about this high-fat diet when I was running when I was 20 or so, because my career would have been very different. I would have run many more ultra marathons successfully, because I just tailed off very quickly. As the more carbs I ate, the more pre-diabetic I became, and the worse my running went. I was just tell you that lovely story. So one of the Indian diplomats in Cape Town, I've become a great friend of his. And Indian people, as you know, eat vegetarian diets. And he read about this low-carb diet, and he was a runner, and he wondered, wonder what happens if I switch from being a vegetarian. So I said, well, it's not going to harm you, it might help. And he switched to become a carnivore, an Indian carnivore. And he said it's terribly difficult, because whenever I have all my friends from India come out to meet me, or the other important people from India, we have to provide them with the conventional vegetarian diet. So he's converted to this diet. His performances are just going up and up and up. And he sends me an email every few months as he's done another race. And the funny thing is, the people he trains with eat high carb diets. And when they race, he just leaves them all behind. So, and they can't understand. They say, but how can you run like that if you're not taking in carbs? They just don't get it. So let me tell you what I would like, a study I would love to do was to see what happens if you're high carb adapted after 3 hours of exercise. Because if you're going along burning, you suddenly run out of glycogen. You can't burn fat, because fat, your body's not designed to burn fat. You have to slow down. You absolutely have to slow down. But if you're burning fat from the start, you're fine, because your 1 to 2 grams of fat is going to get you right through 3 or 4 or 5 hours. So at the moment, I don't believe that your diet plays any role in your performance. That's an important point to make. Industry made us believe that carbs make a difference, and we've shown they don't. However, if you could get athletes to do 4 or 5 hours of exercise, I would like to see what happens in a carb-adapted athlete. They're going along, and then they run out of carbs. What do? Whereas if you're burning fat, you shouldn't have a crisis. You should be able to go on. The problem is no one will run on a treadmill for 4 hours or 5 hours. So we tried it. We tried a cycling exercise for up to 8 hours, and we actually did find evidence that the high-fat group were doing better, but we only had a few numbers. So the reason I want to do that is because I think that you're healthier if you're eating a high-fat diet. And I would also make the point that all the studies in laboratories are one-off races. What happens over a season? Mm-hmm. That's the other question that needs to be answered. And I think your body's more inflamed if you're burning carbohydrates. Dave Scott said that. He said he will not tell any of his athletes to eat a high carbohydrate diet, because their bodies are always inflamed and they're more likely to get injured.
I'm sure there are some athletes listening to this who may be interested in an 8-hour treadmill endeavor. But we have people in our audience like Mike McKnight, who he ran a 100-mile race completely fasted, and showed with glucose data that his body was able to super effectively manage that situation. And clearly he was doing that entirely on, or almost entirely on fat. I think the next question and last question I wanted to wrap on is a really nice mesh with what you were just describing with the research, what we need to show next. And I think it's that we're seeing the ability to take the lab equipment measurement systems and put them on the body directly. And now they're mobile, and now we can start to log data in much more interesting environments. And I think the continuous glucose monitor is an example of this. But I would love to ask you, what molecules, in addition to continuous glucose data, would you want to see tracked continuously? If you could just wave a magic wand and you could measure anything about the body, and you wanted to do so to demonstrate the metabolic conditions for best metabolic health and also how they affect performance, what other molecules would you be looking at?
Yeah, I think fat oxidation is the key. It's a very important factor. The more fat you can oxidize, probably the healthier you are. So that's something I would look. And we actually in about 1976, we had guys breathing into and measured their gas exchange in a 56-kilometer race. But we used such archaic equipment that we didn't get real proper data. So I don't think there's an individual molecule that you can look at that's as helpful as glucose at the moment. But if you could measure your glucose and your fat oxidation at the same time, that would be really helpful. And you could then classify people into the different levels of carbohydrate oxidation, fat oxidation during exercise, and see what happens, and also see how it tracks over duration. So my prediction is that if you're a carb-adapted athlete and we ask you to run for 4 or 5 hours, you're going to hit some sort of plateau when you run out of glycogen. And if you're not fat adapted, you're not going to be able to burn the fat as effectively as if you were fat adapted. And that's where the difference will become apparent. And then, of course, it extends out further. Now, the athlete you mentioned, we have an athlete in Cape Town who cycles about 150 kilometers a day and eats zero carbohydrate. Now, the biologists will tell you it's impossible, but it isn't, because because they say you can't convert fat to glucose in the liver. And I'm convinced you do. That's where you can generate your glucose from fat, is in the liver. And I suspect that that's happening with these athletes who do not need to eat anything during a 100-mile race. They have to become hypoglycemic. And if they don't, it's because they're converting fat into glucose, blood glucose. And if you're doing that, then you've solved the problem. You no longer have a metabolic issue during exercise. You can go on forever because you've got lots of fat and you've got enough glucose to keep you going.
Well, I think that's as interesting a topic of research as any, but and also a really fascinating, I think, cliffhanger that hopefully we'll be able to have another conversation and discuss some results in this area sometime soon. This has been amazing. I'm really excited to continue to follow along with your work, and I appreciate you coming and joining A Whole New Level. Thanks for making this happen, and thanks for continuing to push forward on the science here. It's amazing, and it's informative, and I love that it's the cutting edge right now.
Thanks, Josh. Well, it's been lovely, and thank you for thinking it through and asking all the relevant questions that I could answer as best I could. And I think we got a message out there. And a lot of people are saying that actually they're going to begin to accept what we found. There's going to be resistance because people's careers have been built on saying carbohydrates are important. But be like me. They need to be like me and just say, okay, I got it wrong. Let's move on. That's the way to do it. And the quicker we do that, the quicker we get the message out to the athletes that they don't need to eat all this carbohydrate, and that such a high carbohydrate diet is going to harm the health of most of them in the long term. That's the message that we need to get out.